Okay, let's continue. The second part of my lecture is dedicated to the identification of quarks and gluons and also to hadrons. In contrast to leptons, quarks feel the strong interactions mediated by gluons. Uh, Gluons and quarks, they are not seen in the detector due to their confinement property. However, they can hadronize into mesons or baryons, and at high energies, much higher than the quark mass, initial quark or gluon will produce a jet of hadrons. Gluon and quark jets are not so easy to distinguish. Gluon jet tends to be wider and have softer particle spectrum. As the event display at the right, you can see the jets since produced by two quarks or gluons, hard to say. To reconstruct jets, we have to sum up the particles produced by this particular jet or assigned to the jet. Typically, the jets reconstructed using a conical cut around the direction of a so-called seed particles or fastest hadron, or another method is to interactively add up pairs of particles that give the lowest invariant mass. We can even separate different quark flavor, at least statistically, by looking for displaced tracks from B and charm hadrons inside jets. Remember, B and charm hadrons, they live finite time and can travel some distance away from the primary vertex, such that you can see the secondary vertex, which you can, depending on the detector, either you can directly reconstruct this secondary vertex inside the jet, or you could look at the distribution of the impact parameter, and the impact parameter of the displaced tracks originated from this secondary vertex, they will have non-zero value with respect to the primary vertex. In addition, looking at the how wide is the jet, you could also use these jet properties to discriminate between quarks and gluons, and to approximate the momenta and direction of quark and gluon jets. Recently developed method, particle flow method, allowed to improve the quality of the jet reconstruction. In a typical jet, about 60% of the jet energy is from charged hadrons. 30% is from photons. These protons are mainly produced in the case of neutral mesons, pi-zero mesons primarily, and 10% of the jet energy comes from neutral hadrons, such as neutron or k-zero long. The traditional approach to the jet reconstruction in the past was to measure all of the jet energy in the calorimeters. Therefore, you could expect that 70% of jet is measured in h-cal, which is the sum of 60% of energy from charged hadrons and 10% from neutral hadrons. Typical h-cal, they has rather poor jet resolution, which is at best of an order of 50-60% over square root of E, and this is a main limiting factor which limits the jet resolution. In particle flow approach, the idea is to measure the energy of charged hadrons in the tracker, which has by far better energy resolution by looking at the curvature of the tracks produced by charged hadrons in the magnetic field. Photons you measure in electromagnetic calorimeter, which has by far much better resolution than h-cal, and only neutral hadrons, like neutron or k-zero long, you measure the energy in the h-cal. In such approach, only 10% of jet energy is taken from h-cal. And in this case, the jet energy resolution can be improved to be better than even 30% of the square root of E. At the right, you could see the simulated events, and you could see the energy of the jet, which is made of energy of electromagnetic calorimeter and hadronic calorimeter. Without usage of tracking and with usage of tracker to measure energy of the charged hadrons. Then the main remaining contribution to the jet energy resolution comes from the confusion of contribution from tracking electromagnetic calorimeter and hadronic calorimeter from the overlapping showers. So in order to improve this, you have to you have to construct calorimeters with very good or high granularity to help the very complicated pattern recognition to discriminate between the contribution to the energy from tracking and calorimetry. This approach is being studied for detectors in the future plus and minus linear colliders, ILC or CLIC. You see here the example of simulated events in the ILC detector. So, we just discussed how to approximate the properties of quarks and gluons, because gluons and quarks, they cannot be seen in the free state, but we can measure the jets produced by quarks and gluons. What about hadrons? Instead of making do with jet reconstruction, often the physics understudy requires the identification of individual hadrons. Most hadrons are short-lived and unstable and decay into few long-lived particles. There are only very few long-lived particles, long-lived from the point of view of the detector. The typical length of the detector is a few meters. Now let's see at the average travel distance for various particles. It is shown in this table. You see pion with its mass of 140 MeV mainly decay into muon and neutrino. It has a lifetime of an order of 2.10 to minus 8 seconds, resulting in the C tau of about 8 meters, so stable from the point of view of the detector. The same is true for kaon to a lesser extent, but still the C tau for kaon due to shorter lifetime is slightly less than 4 meters. K0 short travels an average 2.7 meters. K0 long has very long distance, traveling distance. Proton, being the lightest baryon, is stable, it doesn't decay. The experimental limit on the proton lifetime is more than 10 to 34 years. Neutron, it can decay, but still lifetime is very long, and the travel distance is very long. Lambda travels around 8 centimeters before decay in average. So all these particles, I would say, they're all stable. Well, K0 short and lambda not completely, and K0 short decays to pi plus pi minus primarily, and lambda decays to proton and pion. These two particles, they are called V-zeros because they can be seen as the vertex in the detector, two-pronged decay vertex. The example of the Atlas event display is shown at the left, and you see here the K0 short shown in red, which decays to pi plus pi minus. V-zeros can be reconstructed looking at the kinematics of the positively and negatively charged decay products without needing even to identify whether the daughter particles are pion or proton. Here you see the so-called Armenteros plot from Atlas. Y-axis corresponds to the PT of positive particles, and x-axis shows the difference, longitudinal component of the momentum, difference with respect to the sum of the PL plus and PL minus. Think yourself what is shown here, where is K0 short and where is lambdas. So we discussed V zeros, they are neutral. What about other neutral hadrons? These are K0 long and neutrons. These are stable from the point of view of the detector, and they are detected in the hadronic calorimeter. Both feel the strong force, and when incident at high energy onto a matter, they produce hadronic showers. Relevant scale of nuclear interaction, if you remember, is, say, for iron it is about 17 centimeter. So hadronic showers are much longer than electromagnetic showers, and hadronic calorimeter, which sits behind electromagnetic calorimeter, is much larger and heavier than equal. Let's now summarize what we discussed so far. Typical high-energy physics detector consists of the few parts, starting from innermost tracking chamber, then electromagnetic calorimeter, then hadron calorimeter, and in the end, muon chamber. Let's now briefly discuss how different particles, interact in these detectors. Photons, they are neutral, they have no tracks and tracking chamber, and they deposit all their energy in the electromagnetic calorimeters. Electrons and positrons, they are charged particles, they ionize the tracking chamber and can see there the trajectory. And they also deposit all the energy in the electromagnetic calorimetry. Just know that the electromagnetic shower initiated by electrons starts longer than the shower initiated by photons, just because electron or positron entering into the electromagnetic calorimeter, they to first emit the Bremsstrahlung photon, which will then start the shower. Muons, they have no strong interactions, and electromagnetic interactions is much weaker than in case of electron due to higher mass of muons. Therefore, muons penetrate through all detectors, and only muons are seen in the muon chambers, which is in the end of any detector. Charged pions and protons, they do have track in the tracking chamber. They leave only small amount of energy in the electromagnetic calorimeter, and they produce hadronic shower, which is absorbed in the hadronic calorimeter material before reaching the muon chamber. Finally, neutrons, they have main activity in the hadron calorimeter. So any general purpose detector is made of this detector which we just discussed. Example is shown here for the slice of the CMS detector. You see it starts with a silicon tracker, then electromagnetic calorimeter made of crystals of lead tungstenite, then hadron calorimeter, all this inside magnetic field. You see the superconducting solenoid, followed by the muon detector, also magnetized, but with a different polarity compared to the tracking detector inside the main solenoid, and you see the muon track passing through all the detectors. So general purpose detectors like ATLAS and CMS, they work, they search for, they study particles with high mass, and therefore in this mass range it is not so important to identify different charge hadrons like pion, kaon, and proton. Therefore, this calorimeter is missing one particularly useful for pion-cation discrimination device Cherenkov counter. In some experiments, the identification of charge hadrons is of particular importance. Charge hadrons, pion, cation, and proton, they are all effectively stable and have very similar interactions with the signature of track in the tracking chamber and hadronic shower in the electromagnetic calorimeter. If it is somehow crucial to discriminate between them, you have to do something else. Let me show you the example of the hadronic decay of fire methods into a pair of K plus, K minus. And if you look at the reconstruction of this decay in the Selex experiment, without cation identification, you see some peak of phi sitting on the very large background due to two-track random combination, combinatorial combination. And this background is mainly populated by pions from other sources. If you now switch on cation identification and identify the two tracks as cation, this will suppress significantly the background from pion decay, and as a result you see that the signal to background ratio is much improved. The hadron ID is even more important in B physics to study the hadrons containing the big quark. Well, B physics can shed light on the reason why universe is dominated by matter, and for that you have to study the violation of symmetry between matter and antimatter, which is called CP violation. And one of the example of such violation is given by the comparing the decays of B0 to K plus P minus and B0 to K minus pi plus, which has opposite CP. If one makes combination of all two-body B decays, you can see the many different overlapping contribution from various final states. If you now apply, it is shown at the top right figure. If you apply particle ID and if you will be able to discriminate in particular between pions and kaons, you see that the signal to background ratio is dramatically improved, and you could easily discriminate between B decay to 2 pion shown in red and B decay to pion and kaon shown in blue as a result of this particle identification. So now let's look at the example of the dedicated detector, which is LHCb. It is a detector made specifically to study B physics and also charm physics at Large Hadron Collider. The LHCb looks like a slice of the CMS detector with one important difference. There are two extra detectors for identifying charge hadrons, reach 1 and reach 2. We will be discussing how it works in the third part of my lecture. Now let me conclude the second part with a short quiz again. How to identify quarks and gluons. Give examples of stable and unstable hadrons from the point of view of a particle detector. Give examples of neutral hadrons and identify lambda and k short at slide 22.